In this video, I'll be showing you guys how to solve for the volumes of shapes as a function revolves around the y-axis. So I put washer here as it's just quite a more general term for using rather than disks. But basically, I already have a video that describes how to find washers and disks about the x-axis. It describes it very well. I'll put a link down in the description for you guys if you're curious, because I highly recommend that you watch that first if you don't know what a washer or disk already is. So, about the y-axis is very similar to the washer and disk about the x-axis. So, it's a pi with your function that bounds to the right squared minus your function that bounds to the left squared. And keep in mind, your dependent variables, your independent variables now, for your functions are y. So you need to switch your functions so that they are dependent on y, or with respect to y. So this right here is the general formula. We're going to do some problems to show you how to do this. Let's go ahead and find the volume by revolution of the region bounded by these two functions. So if I were to draw a kind of 3D map of what's going on here, let's go ahead and call this your parabola. This is x squared in this case. This is your x and y axis, and this is your z axis. And your function y equals 4 is just a straight line at y equals 4. This is y equals x squared. And we have to rotate this region bounded by your two functions about the y-axis. So that means we're rotating this guy around like so. That's why I included the z-axis so you can see the 3D example. We're simply just spinning this along the bottom of this parabola. We're going to find the volume of that region, of this shape created by this region. Well, in order to do this, we need to realize an important fact. Spinning this entire region about the x-axis, about the y-axis, is the same as spinning this half the region about the y-axis. So if I were to draw the new function, what it looks like, we can kind of just ignore this half here. Here, let's draw this out. We can kind of just ignore this side here, right? So if we have this entire region shaded in, we can kind of ignore one of the sides, so we just need to care about one of these. Because if we spin this region around the y-axis, it'd be the same as spinning the entire region around the y-axis. This is important to know, because in order to get your functions with respect to y, you simply need to isolate y. Let's go ahead and isolate y here. Y equals x squared turns into the square root of y is equal to x. Technically, there should be a plus or minus, but we can kind of just ignore that plus or minus. And if we have just the square root of y as a function of x, really our function just looks like this, where it cuts off at the origin. This is a function for the square root of y. All right, now that we have that, how about the left bound? Well, the left bound is simply x equals 0. It's a straight line at the y-axis, and this straight line is your left bound of this region here. All right, so if we set up our integral pi, our right function bound is of the region is this guy, which is square root of y squared, minus our left function boundary of our region, and our left function boundary is simply 0. So if your left bound is 0, then it's just a disk. So we can kind of just ignore it. Therefore, your integral looks like this. And what are the bounds of the integral? They're from 0. Since the bounds of your integral are now with respect to y, you need to write down the y values that are bounded, that bound your region. So right here is the first y boundary at the origin, where y is equal to 0, and the upper boundary is y is equal to 4, right, given in this problem. So the bounds of this integral are simply 0 and 4. Alright, if we just basically simplify this integral, we just get 0 and 4 for the function, y is the integrand. Therefore, the antiderivative is y squared over 2, technically times pi, from 4 to 0. If we plug in 4, we get 16 over 2, which is 8 pi. If we plug in 0, we get nothing. Therefore, the boundary of this region revolved around the y-axis is 8 pi. So keep in mind, if you're revolving something around the y-axis, you now need to isolate y in your variables. Your functions must be functions of y. So we isolated y here to get the square root of y is equal to x. And we isolated y here. It's already isolated, y is equal to 4. And we use those as our boundaries. Now, y is equal to 4 in this case is not any left or right bound. It was the upper bound for our integral. Let's go ahead and find the volume of the region bounded by these functions. So first thing we want to do, we want to draw out our graph. So the graph square root of x looks like this. The graph x equals 4 is simply a vertical line at x equals 4. And the graph y equals 0 is simply a horizontal line at the x-axis. So we want to rotate this region about the y-axis. Well, how do we do this? Let's go ahead and set up the integral. Actually, not set up the integral yet. We need to find the functions. So y equals the square root of x is equal to y squared is equal to x. Y is equal to 0 and x is equal to 4. So this right here, all these functions are already isolated. We can't really do anything with these three functions anymore. So we need to take these as face value and then use them in our integral. So pi times the integral of the function bounding to the right. Well, the function bounding to the right is just 4. X is equal to 4. Right? This is the function that is bounding this region to the right now. So 4 squared is the function that bounds to the right, minus the function that bounds the region to the left. Well, the function that bounds the region to the left of this is, well, square root of x. But I have to isolate y in this case, so we have y squared instead as our function that bounds to the left, dy. Now, all we need to do is find the upper and lower bounds of our integration. Well, the y values that bound from the bottom and the top are 0, since y is equal to 0, bounds this region at the bottom, and this point right here. This is the highest y value that we can reach. Well, how do we do that? Well, how do we find this? Well, we know that x is equal to 4 and y is equal to the square root of x intersect at this point. Therefore, if x has to equal 4 at all these points, y is just simply equal to the square root of 4, which means y is equal to 2 at this point. So the upper bound of the y value is 2. Now that we have that, we can just simply solve for this integral. So integral simplified 0 to 16 minus y to the power of 4 dy is equal to pi times 16y minus y to the power of 5 over 5 from 0 to 2. If we plug everything in, we just get pi times 32 minus 32 over 5. Let's go ahead and find the volume of the region revolved around the y-axis bounded by these functions. So first things first, let's draw the functions. Well, y is equal to 2x is a linear line with slope 2. Y is equal to 0 is again just along the x-axis. And x is equal to 2 is a straight line at x is equal to 2. And this right here is our region. So we want to rotate this around the y-axis. How do we do that? Well, we need to find the right bound function and the left bound functions all with respect to y. So y is equal to 2x. How do we isolate y in this case? Well, y is equal to 2x is simply y over 2 is equal to x. The rest of our bounds are already isolated. X is equal to 2 here. So let's go ahead and write our integral. So our integral is the right bound of our function. Well, the right bound is x is equal to 2. So 2 right here is the function that bounds the right side of this region, minus the function that bounds to the left, which is y is equal to x2. But we isolated y is equal to x2 to get y over 2 is equal to x. And we need to square this. So what are our bounds, upper and lower bounds for this function? Well, the lower bound is 0, bounded by y is equal to 0. And our upper bound is at this point here. Well, this point is the intersection point between x is equal to 2 and y is equal to 2x. Therefore, y is equal to 2 times 2. Right? The x value is at 2 at this point, then we just plug in 2 into this function. So y is equal to 4 here. Therefore, our upper bound is 4. So if we simplify this function, this integral, we get 0 to 4, 4 minus y squared over 4 dy. And the antiderivative is pi times 4y minus y to the power of 3 over 12 dy. Sorry, not dy anymore. 0 to 4. Alright, all we really need to do is plug in for 4 and 0. Well, plugging in for 0 will get us nothing. So just plugging in for 4 will work. 16 minus 64 over 12. Now, if you wanted to, well, what's it called? Simplify this fraction, then it would be 16 over 3. So, therefore, this is the volume of revolution about the y-axis. So really, the only difference is that your functions are isolated now with respect to y. Right? You just need to isolate x. Wait, have I been saying isolate y throughout the entire video? I feel like I have. Well, the math works, but as always, if you have any questions, put it in the comment section. And if you found this video helpful, consider subscribing and liking the video. Thank you for watching.